everybody, how you doing? Animal Crossing, I haven't played it. Is that the game where you farm? Or wait, that's Harvest Moon, isn't it? But is it the same people that make that? We kill animals? No. Design a controller to farm gold in RuneScape. I'm sure people did that back in the day. Join the UB Minecraft server. There's no killing in Animal Crossing. UB has a Minecraft server. Selling your soul for bells. Someone is building Capon in Minecraft. Capon Library. Alright, we'll give it about one more minute. Have I played Monster Hunter World? I have a Monster Hunter game for Nintendo DS, but I can't remember which one it is. And I didn't play it too much. My buddy had a roommate who would eat dinner every day with 4 tabs of RuneScape open, grinding for gold on separate accounts. That's true, Tim. They are building Capon in real life as well. I wonder when they'll be done. Oh, Danny Colucci. The project is an April Fool's joke, right? It is April 1st, which is April Fool's Day, so you shouldn't be gullible on this day. But that project is real. That's real. Do I play Smash? I played the N64. We have a Switch. So isn't there a new Smash out on Switch? I don't have that one though. Alright guys, it's 12:05. So we're gonna get started on this. We can talk more games when we wrap up. Okay. Any update on exam 1 grades? Those are supposed to be up today. I'll double check with our teaching assistant, but those are supposed to be up today. Quarantine Spoon says, uh-oh. They're probably fine. Don't stress about that. Okay, so first thing off, I put up Project 1, and that's up on UB Learns, so go check it out. It'll be cool. You're designing a controller for a 6-volt DC motor, one that we used in class, and you now have the skills to do that. So like, if you look at the project, I give you some performance constraints on like settling time, rise time, stuff like that. So you have to build me a controller that satisfies those constraints. And then, so it's going to be due in 2 weeks from today. So Wednesday the 15th. And my plan is, when you guys turn those in, you know, there's not a unique answer to this. Like, everybody should be coming up with different controllers. We can try out the controllers in class that day. Like, if you want me to run yours on the motor, I can do that, and we can see how it does. So that'll be pretty sweet. I'm looking forward to it. We did that last spring, and people enjoyed that. But as far as course content, we're now going to move beyond the root locus method. So let's recap right here what we can do with the root locus method. And then I'm gonna say like some of the benefits of this, but then why we also want to study some other techniques, specifically state space. So I've showed you this a couple times, you're familiar with it, but let's just drive it home. You start with performance criteria. So we got like, you know, overshoot, settling time, rise time, and then you have some steady state metrics like KP, KV. And sometimes you even choose your sampling period. So that's capital T. And then where we go with this is we choose some target closed loop poles. So this describes the dynamics of our feedback system. And we've been calling these like Z star. Now, using the root locus method, given those target poles, we've been designing controllers that look like this.
Do you see now? It means becoming like clear water.
But if you wanted to make this controller a little bit more complex, there's no reason, and you'll see this with Project 1, you can have like a couple poles, a couple zeros, I mean, and a couple poles. So like for Project 1, I want you to make a controller that has 1 0 but 2 poles this time. And you can use the same techniques we've been doing all along. The angle criterion, magnitude criterion, to figure out what those should be. Then, once you have this, the final step in the selection of Z star, how would you go about selecting the best target poles? So that's a little subjective. So if somebody gives you some performance criteria, here's an example. You might think that it's best to exceed their performance by a lot. Like let's say they have a settling time and they're like, look, I need a settling time of 1 second or less. And you say, okay, well, I'm going to give you something that does it in 0.1 seconds. That might not always be the best choice, because if you make a system way faster, it's going to use more control amplitude, so like maybe more torque or more voltage, so it might use more energy. So usually when you're selecting your target poles, it's good to start with something that satisfies the performance constraints but doesn't like exceed them by a lot, because performance constraints are set for a reason. Sometimes it's good to far exceed them, but it's really case by case. So it's hard to say like, how do you choose the best target poles? All right, when you have your controller, remember that your control input, U of Z, is your controller times the error that's coming in. And if you use backward shifting theorem on this, this is like the line of code that you're going to put in your microcontroller. It's going to be my control input at this time, step K, is going to be like something times the previous control plus like something times the previous error, maybe times the error like another time step prior. And so it'll look different, but the point is, once you make this controller, you can convert it into a difference equation that the computer can read. And in a nutshell, that's what you're already capable of right now. So Project 1 is your chance to go through that process, stem to stern on a new problem. So root locus method is great. Look at this box. but it's best, I think, for single input, single output, also known as CISO systems. So this is like you're measuring one thing, you're trying to control one thing, and you have one input that does it. So like with that antenna, we said that I'm controlling the azimuth angle and I'm controlling it with a torque. So it's like the azimuth angle is your one output, the torque is your one input. And for project one, you have one input, which is a voltage, and you have one output, which is an angular velocity. Root locus method is really great for these kinds of systems, so you can like pretty quickly put together a decent controller. Root locus is also good for systems where you can directly measure that single output that I'm talking about. But you can't, that sounds kind of basic, but you can't take it for granted. So what I mean is, say I'm controlling the azimuth angle. Root locus is great if I can measure that azimuth angle directly. But in some control applications, it's a luxury to actually be able to directly measure with the sensor the quantity that you're trying to control. Oh, I have a good example. Okay, I'm going to show you this guy because I really like these. Let's see if I can get the camera. Okay, so this, you've seen it before. This is our little self-balancing robot that I bought off of Amazon. So the sensor, the goal of this is to balance, you know that. The sensor on here is maybe, okay, you can kind of see it right here. It's this blue chip is the sensor. And it's got a gyroscope on here. And it has accelerometers as well. But let's just talk about the gyroscope. Yeah, IMU. The gyroscope measures angular velocity. It doesn't directly measure the pitch angle of this robot. It measures the rate at which it's pitching. Now, when they control this, they use the accelerometers to try to estimate the pitch angle as well, but you could control this just measuring the angular rate. So that's interesting because in that case, like you're trying to control the angle so that it stands upright, but you're not measuring it directly. You're measuring the rate at which it pitches. You can't really... So that's just an example of where you're not directly measuring what you're trying to control. So root locus is good when you can directly measure that quantity. State space, you don't need to do that. So state space techniques are more generally applicable. So the first point is state space is useful for multiple input, multiple output systems. You may be controlling more than one output at once on a system. And you might be using a combination of different actuators to control all those different outputs. It's like you're juggling multiple balls at once or something. I don't really have a super great example of a multiple input, multiple output system off the top of my head right now, actually. Maybe you guys can come up with something. Okay, then state space is useful Ooh, 2 degree of system spring mass damper, where you might be controlling the position of two masses at once, and they're connected by a spring, and maybe you have like a force that you can apply to both of these independently. So that one would be like 2 inputs, 2 outputs. Jonathan says a UAV in flight dynamics. Okay, good. Like flight dynamics, you have your angle of attack, your airspeed, your altitude, your roll angle. You might be trying to get all of those dialed into a specific value at once, and you're doing that by controlling multiple things at once, right? Because you have the rudder, you have the thrust, you have the ailerons, elevator. So it's like you have a bunch of different control surfaces on an aircraft that all work together to help you control multiple things about this aircraft. Shoot, maybe we should do that as a project. What do you guys think? Project 2? So that's a perfect example. So state space is useful for that. Like, how do you make all these things work together to control a bunch of stuff at once? Okay, so state space is useful also when you can't directly measure what you want to control. Haven't taken flight dynamics, so I'm against it. So we're going to get into this pretty soon, but when we use state space, there's something we use called an estimator. An estimator estimates what we can't directly measure. And then we use that to help us control. So we'll get more back to this, but I just wanted to quickly motivate, why would we go to state space if we already know one way to make a controller? Well, root locus isn't going to help us in every situation. We have to have a little more of a diverse toolbox. Probably you guys have worked with state space before, but we're going to go through the basics. There's 2 equations you work with state space, okay? There is the output equation, and there's the state equation. Is an estimator the same as an observer? The answer is yes. So because I have some of these equations typeset, I want to show you what these equations looks like when I'm going to be writing them by hand. So these are vector equations in general. And so there's matrices and vectors in here. When I type something in boldface, that's a vector. But when I write vectors by hand, I like to just put a little underline on them. I know some people put like arrows on top. An arrow just takes too much effort. You got to draw a line and then the other little squiggle thing. We got to simplify that process. So this is how I would write the output equation. So all of this underlined stuff, these are vectors. In the table below, we'll talk about what they're called. And then these C and D, these capitalized things, they're matrices. All right, most of you know this. And the way I'm going to do the state equation, I'll underline that. All right. So we have a state equation, we have an output equation. This is how I'm going to typeset them or write them by hand. Let's define each of these. So yk, a vector, you could have a bunch of outputs. This is your output vector. And the dimension of this is going to be m by 1. So it's a column vector, and m is your number of outputs. So if you're just doing a single output system, m will be 1. If you have 2 outputs, it'll be 2. So on and so forth. Okay, u. This is our control vector. So it's just like your control signal, but we could have more than one. So the example of an aircraft is perfect. It could be the angles of multiple control surfaces and the magnitude of the thrust or something like that. So this is also a column vector where r is the number of inputs. Okay, x, this is so inputs and outputs, we've done that with transfer functions. So x is the new thing that state space generates, and it's appropriate that this is the state vector. This is dimension n by 1. N is the number of states. There's multiple ways to describe what a state is, but it's the minimum number of variables that can describe the dynamics of your system. It turns out to be equal to the number of poles of your transfer function. So like if you have a second order system that has 2 poles, it's going to have 2 states when we go to a state space representation. And that's the way I would think of it for now. Okay, then the next 4 things are the matrices in the state space equations. So the way I write these by hand, it's just the same. Capital C, D, A, B. This C, we just call it the output matrix. First, I'll name all these, and then I want you guys to practice your linear algebra. And over here, write the dimension of each of these matrices. Is it number of poles of the closed loop system or closed loop poles of the plant? For the A matrix, well, it depends on what we're describing, because we're going to have an A matrix for the plant. We're also going to have an A matrix for the closed loop system. So the A matrix for sorry, why am I talking about A matrix? Well, the state vector for the plant has the same number of states as you have poles for the plant. Okay, so C is called the output matrix. D is called the direct transmission matrix. I see eigenvalue being spoken of in the chat. We'll get to that. A is your system matrix. And B is your control influence matrix. So we have some new terminology for state space. Okay, so now let's get on to the dimension of these matrices, because this is going to become very important later on for like debugging things, making sure that the the dimensions of all these matrices are correct. So let's calculate this. Let's start with the output matrix. Like, what size should that matrix be in terms of M, R, N? Chris says 2, but that's you got to give me 2 dimensions. You got to give me the number of rows and the number of columns. M by N. Do you guys agree? So the way to check, let's look at this equation. This is where the C matrix comes in, right? So Y is M by 1. U is R by 1. X is N by 1. So you can only add vectors of the same size together. So, and we know that when we add these results on the right-hand side, it needs to come out to an M by 1 vector, because it has to be equal to Y. So I know that this product has to be M by 1. This product also has to be M by 1. So the question is, like, if we look at this D times U, I'm going to have some matrix of some size times an R by 1 gives me an M by 1. So a quick way to do this, I know that this has to be M by R, because in order to do matrix multiplication, this dimension has to be the same in order for them to be compatible. And then this is the resulting dimension of the product, which I know has to be M by 1. So that means D has to be M by R. C is going to have to be M by N, because it has to give an M by 1. Okay, so this is going to be M by N. This one's going to be M by R. And I don't want to spend too much time here because we got a lot more to get to, but you can verify this for yourself later. The system matrix has to be N by N, and the control influence matrix has to be N by R. All right, here's our terminology. Let's move on. So the first thing I want to show you is how you can convert between a transfer function and put it in state space form. Okay, because this is just another way to represent our system. So up here, I have a generic transfer function, and it turns out there's an infinite number of state space representations to represent the same transfer function. So I could come up with an infinite number of like A, B, C, D matrices that can do this. But we're going to focus on one specific representation that's useful for control design, and that's why we call it controllable canonical form. So this right here is going to be our A matrix. And I'm just going to quickly give you the definition of this, and then we're going to do an example to put a transfer function in controllable canonical form. So it's going to look like this: 0, 1, 0, and then this represents like ... There could be a bunch of columns in between here, and then we go 0. Then this is going to be 0, 0, 1, ... 0. Well, really, there's going to be a 0 here and then more ... just to be clear. And then these zeros keep going down here. until you get to the second to last row, and then there's a 0 there. 0. And there should be a 0 below this, and then 0. Is the music too loud? Ooh, did I not turn that down enough? I'll turn it down more. Okay. Then this keeps becoming zeros until it gets to the second last row, and then it's 1. This is just zeros going across here until you get to the 1. And then here's what the bottom row is. It's minus a n minus a n minus 1 minus a n minus 2 dot 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 all the way to minus a1. And these a coefficients are coming from the denominator of that transfer function. So this will make more sense when we do an example, but okay, here's your control influence matrix. This one's easy. It's 0, 0, it's all the way 0, and then the last element's 1. This is for, I should have said this. This is for single input, single output for now. You can tell this is single input because the dimension of B is n by r, and we just have one column, so r equals 1 in this case, and r is number of inputs. Is A 3, 4 going to be a 1? 3, no, this is, well, this diagonal, yeah, this 1 like carries all the way down to there. You're right. A 3, 4 will be a 1. Yep. So it's kind of like you have this diagonal of 1s, and then you're going to have 0s above it, 0s below it, until you get to the very last row. And then you just have those A coefficients. All right. C. This one's a little more, it's Bn minus An B naught for the first one. I'm gonna run out of room here. Shoot. This element, I'll try to zoom in. Bn minus 1 minus An minus 1 times B naught. And this trend kind of continues until you just have, at the very last entry, you have B1 minus A1 B naught. And your D matrix, which isn't really a matrix, it's just a scalar in this case, it's B naught. Okay, so let's do an example to have this make a little more sense, okay? So I have a transfer function here that I want to convert to controllable canonical form. The first thing you want to do is you want to write this in terms of the variables we used up above. So this is going to be like B1 times Z plus B2. And then this is Z plus A1Z plus A2. So I can match these up, like 1 is going to be equal to B1, 1 is also going to be equal to B2. I don't need that. 1.3 is equal to A1, and 0.4 is equal to A2. Now, if you take the generic template up above, why wasn't the first one B naught? Okay, good question. So I'm going to have to zoom in here. Sorry, guys, to swoop in and answer that question. So n is the highest, is the order of the denominator, first of all. Okay. So for the example that we're doing right now, n is equal to 2. So b naught is going to be the coefficient associated with z squared, but the numerator doesn't have a z squared, it just has z to the 1. So we don't have a b naught. B naught's equal to 0. Yep, you're welcome. Okay. So my A matrix, if I take that template and break it down to this size, it's going to look like this. Minus A2, minus A1. And then I can just match this up with up above. So it's going to be 0, 1, minus 0.4, minus 1.3. B is 0. I mean it's easy because it's always going to be zeros and then 1 at the bottom. D is easy. It's equal to B naught. And like we said earlier, B naught in this case is 0. And then C will take a little bit of work. So that's going to be B2 minus A2 B naught, B1 minus A1 B naught. And that's going to be, so B2 is 1. B naught is 0. So like this A2 times B naught is going to be 0. A1 times B naught is going to be 0. So I'm going to have 1 minus 0. And then again, I'm going to have 1 minus 0. So C turns out to be 1, 1. So if we were to write out the full state space model for this, my output equation yk is going to be 1, 1 times xk plus 0 times uk. So you might not even include that. Xk is going to be 0, 1 minus 0.4 minus 1.3 times xk minus 1 plus 0, 1 times uk. All right, so I know I went through that a little bit fast. Once you do a couple examples of this and it starts to click a little bit. Just looking at that transfer function, how can you tell that it's MIMO or CISO? So that means multiple input, multiple output, or single input, single output. The easiest way to tell is to look at the dimension of your B and C matrix. So remember, the number of inputs is R, which is the number of columns of your B matrix. R is number of columns of B, and it's the number of inputs to your system. So I have one column, so I know I have one input. So I'm definitely single input. M is the number of rows of C, And that's the same as the number of outputs. So if you look at, oh, thank you, that should be UK minus 1. So if you look at the number of columns of B, number of rows of C, if you look at that and they're both 1, that means you got one input and one output. I think it's more common to have like one input and then a couple outputs. Having a couple inputs is more rare, but that's the easiest way to check. Look at the dimension of B and C. All right. You are very welcome, Jonathan. What I want to do is scan ahead a little bit. We're running a little bit short on time. So I want to decide how to proceed. What is essential here? So this example, you can convert from state space back to a transfer function. And maybe we'll come back to that later. The way this works is you take the z transform of your state space equation. Yes, you can do that. And when you do some algebraic manipulation, it takes you right back to your original form. But I think this next example is most important for us to show today. This is a property that you got to know. So, and this is an attractive property of state space. The eigenvalues of your A matrix are the poles of your transfer function. So say this transfer function is my plant. It relates my one output to my one input. And this is the same transfer function we were working with up above. So I know the A matrix is 0, 1, minus 0.4, minus 1.3. So the poles we know are the roots of the denominator. Those are the poles. What I'm telling you now is the eigenvalues of this matrix are also the poles. Now, this becomes nice because, whoa, it just got like really dark in here. Either there's a demonic presence or a cloud is going overhead. I'm not sure which. I'm turning on a lamp. Okay. When you have a system that has a lot of poles, it's convenient or it's computationally efficient to calculate those poles as eigenvalues because there's like really efficient routines for that. So let's go into MATLAB really quick and demonstrate this property. Let's just clear this. Okay, so for getting the poles of that transfer function, I take the roots of the denominator. So 1, 1.3, and 0.4. Okay, so those are our poles. My A matrix is 0, 1, minus 0.4, minus 1.3. And if you take the eigenvalues of this matrix using the eig command, you get the same things. Okay? All right. With the last little bit of time, maybe I don't think I can make this code in real time like I want to do because we have just a little bit. But I can show you a code for simulating a state space system in MATLAB. let's go here. Now, a lot of this stuff is stuff you've seen before because I want to compare what we're used to the state space technique. So I'm going to take this same transfer function that we've been working with in these examples, okay? And I'm going to simulate the step response. So there's some question about eigenvalues. I'll get back to that after this, okay? Don't let me forget. So if I want to simulate a unit step response, I'm going to do a vectors of 1. Here's our time vector. So I'm going to simulate for 1 second with a step size of 0.1. So if you use LSIM, we know that's a way to simulate this. Okay. So now let's talk about state space. First thing you do, you make your A, B, C, D matrices. Now there's a couple ways to simulate this. The first way I want to show you is a for loop. So first, what I do is I initialize my vectors. So my state dimension is 2. Your state dimension is the same dimension as your number of poles, like I mentioned earlier. So this system has 2 poles, so I have 2 states. And I just have 1 output. So I'm just making some empty vectors that I can fill this stuff in with. And here's the for loop. Well, first I'm going to make my first output. My output equation is y is c times x plus d times u. Now this notation in here, this means I use all the rows in the first column. So this is matrix multiplication. It's my 1 by 2 C matrix. It's 1 by 2 multiplied by a 2 by 1 vector, and it results in a 1 by 1. And then in the for loop, I just iterate across this. So like, this is my state equation. My state vector at step K is the A matrix times my state vector at the previous step plus B. Ooh, this should also be the previous step. Goodness gracious. And then here's my output equation. Okay, so what I want to do is compare these results. So I'm going to plot my output y from the state space and compare it to the y from the LSIM. Let's put a little break here. So I just want to show you that they turn out to be exactly the same. Let's bring this back. So the red circle is the result from my transfer function using LSIM. The black dot is the result from using state space. So it's exactly the same. Now here's an easier way, which you'll probably use instead of the for loop. You can also use the LSIM command to simulate a state space model. So you can make a state space object in MATLAB just like you make a transfer function object. And so you just say like my system is state space. So here's the command SS. And then you just give the 4 matrices A, B, C, D. And then just like you do for the transfer function, you have to give the sampling period because this is a discrete time state space model. We can talk about this more as we go along, but a discrete time state space model is different than a continuous time. The matrices will be totally different. They'll be the same size, but totally different. And then the way you use LSIM is just like you would with a transfer function. You give your system, you give your input, you give your time. So let's run this, and I'll show you that this simulation gives the same result as well. And now I have like this green square to represent the result we got from LSIM. So you can still use LSIM to simulate this state space model. Okay, so we're going to be talking about state space for the rest of the semester. It's very cool. There's some cool theories that come out of this. Like my favorite probably is related to estimation. So we're going to use state space to predict things that we can't measure. That's a cool concept. But today I just wanted to give you like an intro, show how you can just make a state space model, show that it's an equivalent representation. It gives you the same simulation results if you do a step response and stuff like that. And so we'll officially end this lecture here, but you guys have other questions. I'm happy to answer them. Like, let's go back to, I think Chris and Jean had a similar question. What was that? What do the eigenvalues of the matrix mean? The eigenvalues are the same thing as the poles. So, like what? So it's the same answer as like, what does a pole mean? A pole tells you about the stability of a system. It tells you about the speed, oscillations, rise time, all of that transient behavior. What do the eigenvectors tell you? That one's a little more complex. And you can attack that from different approaches. Let me think. Chris, you would love eigenvectors because you like to go into a deep philosophical plunge. Eigenvectors, that's the way to do it. So one thing we use eigenvectors for is we can represent a system. So like I said, there's an infinite number of state space models. There's a unique state space model for every system, well, for every linear system, that's called the spectral representation, which sounds kind of ghostly. And the spectral representation is this non-physical way of looking at a system where your system states, so what I mean by non-physical, like your system states they can be physical things. Like if you're modeling a spring mass system, your state could be the position of each mass and the velocity of each mass, okay? Those are like very physical things you can measure. But there's no reason that the states have to be physical. You can represent a spring mass system with states that are non-physical. The eigenvectors allow us to build a transformation matrix that transforms our states into the spectral dimension. And in this dimension, the states are totally decoupled. So what I mean by that, like position and velocity for a spring mass system, those depend on each other. You know, if you stretch a spring a certain amount, that creates a force. And over time, that's going to affect the velocity because the spring's going to want to like pull those blocks together. There's a representation of a spring mass system where you can create a state that's something other than velocity and position, and it doesn't affect any of the other states. And they kind of exist independently of each other. And that's where it gets a little philosophical because, this is modal analysis when you get down to it. What was I going to say? Oh, yeah. So I said those states aren't physical, but when you get down to it, these decoupled states are the most concise way of describing what's going on with the system. Yeah, and in modal analysis, you use this to figure out the mode shapes of vibrating objects and stuff. And even though it's not physical, it's the most distilled fundamental way a dynamic system works. Like an analogy I have, and we have eigenvectors for different things. Like um, the way I think of eigenvectors is simplifying something to its most basic features. So like you can look up people use it for facial recognition. They build what are called like eigenfaces, like they're the eigenvectors for somebody's face. And you can if you take a group of faces, what is this? I think it's like principal component analysis, which is like very similar to eigenvectors, or it's the same thing. Um, you can break down human faces into kind of this unique set of features that's not like a nose, a mouth, whatever, but they're like the eigenvectors of a face. And it's like most fundamentally, if you simplify it mathematically to like, what is a face? The eigenvector tells you what it is. I don't know. And I've spent a lot of time looking at them, and I still don't have a very like clean explanation in a intuitive physical sense of what eigenvectors are. Like mathematically, it comes from the eigenvalue problem, where it's like a matrix times its eigenvector is the same thing as an eigenvalue operating on that eigenvector. But what does that mean? You know, Chris, you got to go on a deep dive. Just look up. People have great articles on this, I'm sure. Do you guys have? I saw. Oh, quick. Are there any requirements of the format on the grad student project proposal? Oh yeah, that's right. So graduate students, I want a project proposal by Friday, and this doesn't have to be. So for the format, just give me a couple paragraphs that give me an idea of what you want to do for your project. So the point is, I just want to make sure that you're thinking about it for number one. And then if you, maybe your scope is like too broad right now, and I'll be like, maybe you should dial this back or something. So yeah, just has to be a couple paragraphs. Give me some details, and then I'll give you some feedback moving forward. Can the B matrix be dependent on the states? So the B matrix, well, let's go back. Maybe we'll go back here. The B matrix operates on on your control vector. Now, once we start doing state feedback control, this control input is going to be a function of the states. That's how we do feedback control in state space. But the B matrix itself won't be dependent on the states. If you do the grad project, can it count towards grad classes? No, but it can count towards your individual academic development. And that's very valuable. Can we have a Zoom call with you if needed for project proposal? Yes. Email me and we can set something up. All right. I'm going to see the status of the music. What happened here? Thank you guys for hanging with me here. State space will be cool. See you, Chris. Good luck in your studying. I love this little thing. Sinaris, yes, this is a university class. What will you learn if you stick by? So we're done with lecture today, but this is a digital controls class. You learn how to control stuff like this little robot. If you want to make a self-balancing little dude like this. Did I code this one? No, this one is this is a commercial product. I'm still working on my own. Not quite there yet. This whole COVID thing threw me off track. You learned all that in high school? Yeah, it's fun. Yeah, I heard about that game, Fold It. I think it was like an open source free puzzle game, right? And then people just came in and they played this game Fold It where they folded these proteins to find like a low energy configuration. Okay, it's not open source but free to play. Yeah, and it turns out they found solutions that their simulations and supercomputers didn't find. It was like just humans working on this game that came out yeah. Yeah, Instructables is really great for finding those kind of robot projects. I found this guy. I really like his stuff. What is it? I should bookmark this. Oh yeah, this Jupe Brocking guy. Where's his website? Yeah, go to this guy's website if you want to like do your own digital controls projects. He's got a couple that he just gives awesome instructions. Ooh, electric skateboard. Did Chris leave? Build your own electric skateboard. All the parts. He goes through like control systems and stuff in here. I think this guy's fantastic. Like he's... Where is it? I think this is like the best explanation of the self-balancing robot I've ever seen. And like his schematics are so clean. Oh, the website. I'm gonna throw it in the chat, okay? It's brocking.net. I think my chat blocks, or my bot blocks links. Brocking.net. Brocking.net. Yeah, I just threw that in the chat. Yeah, it's like so clean. He did it with stepper motors, that's right. Like when I was trying to do this myself, I was running into so many problems with stepper motors because they tend to vibrate a lot, and that shakes your whole structure. It shakes your sensors, and so they're giving like these noisy readings. But this guy, he helps with the whole deal. Like I think he does quarter stepping on his robot, so it like if you do micro stepping, like quarter stepping, 8 stepping, it makes it a lot smoother. But when you do quarter stepping and 8 stepping, you have to do more like timing in your code because you have to like send commands faster.
You said bell peppers and beef.
His name's Asimov Solensen. Are you listening to me?
There's no beef in here. So you wouldn't really call it bell peppers and beef now, would you?
Yeah, and then he uses like a little nunchuck, controls it with Bluetooth. He has 3 YouTube videos that go into like all the details. When I first tried it, I was doing full step mode. And then I tried to, so it was shaking a lot. And then when I went into 8 stepping, that requires you to send steps really quickly. And then if you want to send steps really quick, you can't use digital write anymore because digital write is a slow command on Arduino. So you have to do direct port assignment, which takes some work. Professor, you don't need to use a stepper motor. A motor with an encoder will work fine. No, you're right, but they both have advantages and disadvantages. And actually, this guy talks about it a little bit, like why he chose steppers. Like, and it affects the modeling as well. Because like a stepper, you effectively control the angle directly, right? Because every time you send a step, it rotates the motor a specific amount. That's not what happens with a DC motor and an encoder. You control voltage, or PWM, and then that has a first order response with the speed. So it's like, it introduces more dynamics. And a DC motor, its response changes with the amount of voltage that you put through it. So like, there's not one model that describes a DC motor very well. Like even for Project 1, I give you a model for this DC motor, but that one is only accurate over a certain range of voltages, and it's like less accurate at different speeds. So stepper, I think you could get more consistent performance, but it's like, they both come with challenges. A stepper's a little more torquey as well at the low end, so you can make a more zippy, snappy, self-balancing robot with a stepper motor, is my understanding at least. It is not easy to build. He also does UAVs. I'd love to do that. What is this? Oh, he made his own CNC machine. One of those basketball balancing robots. What is that? Like where it spins it up like on a finger or something? Like a basketball player? Oh! 3 motors on a basketball to bounce the robot on top of it. Kind of like BB-8. Welcome, UB Math Professor. We've been raided. Let's look up basketball balancing Arduino thing. Can I find one? Oh yeah, let's try this. We straight up learning. That's pretty cool. The motors for BB-8 are internal though. Doing pretty good. Mark, how are you? You having a good time today? What if outside the frame at the top he's just holding that with his hand? This is not as convincing a video as it could be. How do we know he's not pulling the strings like a puppet? It's just suspicious. Are there other ones like... There's got to be other... Prototype 2. Okay, this one he learned his lesson. Wait, there's a little bit out of frame here. No, he didn't learn his lesson. But he did put some LEDs on here. And that is important. Okay, here we go, here we go. Wow, this is really cool. All right, build me one of these. In the future, this is what I want to do in digital controls. Like we do this and then we do a bunch of these examples. You just completed the path to affiliate. So are you just going to be getting donations all day? This thing's pretty remarkable, I think. Absolutely not. Yeah. The Octo Bouncer? What is this? Look at this thing, it's bench pressing with 4 arms. It just looks, that looks too humanoid. What? Is that a ping pong ball? Oh, that's... Okay, so it's doing image processing. It's got a camera underneath there. These are stepper motors for sure. Grayscale camera. Uh-oh. Looks like an orange racquetball. Oh yeah, it looks too big to be a ping pong ball, doesn't it? Shoot. I don't trust this thing. Oh, we're going back to the bouncing. Ha! Could have done it with 3 arms. Added some redundancy there. Yeah, I don't know. That's pretty sweet.
Если знаешь, откуда и куда ты едешь, я считаю, что это не настоящее путешествие. Настоящее путешествие. Когда ты
But what
давно
about
забыл,
this?
откуда едешь, и ты без понятия,
Can the robot do
где
this?
закончится твой путь. Я верю в это.
I don't think so.
Пластилиновый бег.
Some crazy AI going on there. Okay. Okay, we got a same kind of ball balancing robot here. Looks a little more polished though. He's proving that it's a real soccer ball. Look at it bounce. Oh, but he's not using steppers. He's got brushed DC motors. What if it just falls over directly to the side immediately? Oh, remote control. It's like mind control of the soccer ball. You're gonna go where I tell you.
1, 2, get down.
You could probably do this with humans. Put this device on their head. Active Omni wheel. What? Omni wheel balancing robot, maybe? Yeah, find it for me. Oh, it was the first video of my last search. This one? It's kind of cute. Like, he should put a bird exoskeleton on this. Or like a little hood. Oh shoot, it won't let links go in our chat right now. Maybe I can change that, but I don't remember where I changed that ability. Search Omburo, okay. Omburo. Maybe the capitalization will help me out too. Oh, okay, this. I see. Okay. What's gonna happen? What? What? It looks like it's moonwalking. Oh, the mini rollers. So it's got like little rollers on the side. Ugh. I would call this the Michael Jackson. Yeah. What if we found out Michael Jackson just had a prosthetic limb and it was this? Like, below the knee, this is Michael Jackson's legs. We just never knew. It's struggling a little bit. Ahead of his time. Yeah, there's little mini wheels on the big wheel. Huh. Wheelception. And then if you zoom in on the little wheel, there's hundreds of other little wheels. Fractal wheels. You just keep zooming in and you get to the quantum wheel level. Looks like it has hair up here. There's just like these dangling wires at the top that bounce around a little bit. Ballet dancing? Oh. They really need to put a face and some googly eyes on this. It is hard to get a haircut at this time. Oh man. Romela.org. Where are they? Are they in Rome? Italy? Oh, that's at UCLA. Look at all of these people. There he is. The dynamic anthropomorphic tactile indefector. Dynamic running on multifaceted. Oh, that's like a cheetah leg or something. No. This research needs to be stopped immediately. This needs to be shut down. And it must progress no further from this moment forward. But I love spiders. The opposite is true. What do they say about this? It has the blood, sweat, and tears of all the students who built it. Do you see what they're saying? It consumed. It ate. The very people that worked on it. Carbon fiber tubes, machined aluminum, modular servo actuators, designed to be a base platform on which further systems can be developed. Oh, they wanted to autonomously detonate landmines. That's what they say it's for. This robot's just a pair of legs. It eats, but most importantly, it learns. And this robot's all arms. Oh no, they went further. Oh my gosh. Oh my goodness. No. All right, I'm gonna look this up and then I'm gonna go. But what is? These people need to be stopped. What is this? Is this just a giant spider? No. No, 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 no. I do not like what these people are doing. All right, let's look it up. You really like the look? No, thank you. No. No. Wait, stop the music. You can hear it making little spider sounds. That eye looks so cold and unfeeling. Look at this. Can you imagine this coming down coming down the hallway in your home? Just above you? Oh my goodness. No, thank you. Oh.
The robot naturally tilts its... Note that the robot currently doesn't have a perception system.
You're gonna need a really big metal shoe.
Perfectly, but well enough to succeed on these very...
Alright, I want to see that really long-legged Strider. Wait, do they not have videos of this thing in action? I want to see this. It's first... Oh, no. Duel! This looks like something out of Resident Evil. Blech. No, don't. Oh my goodness. Did you hear him? He's like, that was a beautiful step.
Strider. Self-excited, tripedal, dynamic,
I have
experimental
seen
robot
Tensegrity
by Jeremy
structures.
Easton, Dennis Hong, Yvette Moore walking machine with 3 legs that utilize the concept of actuated passive dynamic.
Wait, what is this?
In pop culture, examples of
Is this
three-legged
supposed to-
robots have emerged throughout the years.
Is this supposed to bring people
The
on
fictional
board?
Three-legged machines were
Oh
described
my
in H.G.
goodness.
Wells' 1898 novel War of the
Didn't you
Worlds
say Half-Life
as alien
2?
tripods and have also appeared in
Java
popular
Lang
video
error.
games.
They were
However,
inspired by
the novel
Half-Life
type
2.
walking robot Strider we present here does not move like any of these fictional three-legged machines.
It moves in a more horrifying
Here,
way than you
we
ever
present the
imagined.
novel tripedal gait used by Strider. Strider begins its step with a stable stance like a camera tripod. As the center of gravity of the robot shifts forward, the robot begins to fall in the direction perpendicular to the pivot line. As the robot falls forward, the middle leg naturally swings between the 2 stance legs using the concept of actuated passive dynamic locomotion. The swing leg then catches the fall, and the robot resets to its original tripod posture.
It kind of reminds me of
preparation for
the
next step.
Strand Beast as well, like that
Here, we
beach
show an
robot.
animation of
You guys know what I'm
Strider
talking
walking
about?
Using the tripedal gait. Note that the body needs to rotate 180 degrees every time it takes a step
Bloop.
to prevent the legs from tangling up. This novel tripedal gait is highly energy efficient, and it uses its built-in dynamics to swing the middle leg between the 2 stance legs. Also, since there are always more than 1 foot in contact with the ground, controlling the robot for stability is relatively easy. Unlike most other legged robots that use the concept of actuated passive dynamic locomotion,
No, no.
optimized design parameters
And
used
then they
for the
make a
first
bigger one.
prototype. To verify our dynamic analysis, a simple experiment of a single tripedal gait was conducted using the first prototype. This shows the comparison between the dynamic simulation and the actual experiment. Exploiting the concept of actuated passive dynamic locomotion, Strider can walk dynamically with high energy efficiency and minimal control.
Are you kidding? Imagine if it actually tried to walk in this field full of rocks. You're telling me it's not going to catch its toe on one of those boulders as it swings it through? It's going to be tripping
Unlike other
all
passive
day.
dynamic walking machines,
How does this thing get up when it
the
falls? That's what I want to
locomotion
know.
robot is inherently stable and can change directions. This video presented our ongoing work on the development of the novel tripedal locomotion robot Strider.
Okay, the other thing I was talking about, I think it's called Strand Beast. Oh yeah, look at it. This one's just totally passive. It's powered by wind. It is a little unsettling. You just see that thing walking towards you on the beach. But look how beautiful it is. Oh my goodness. And he's made a couple robots. Oh my goodness. I think this one's like the elephant. Well, this guy's really cool. They really do move in herds. This one has antennas on it. Dino DNA. No, what? How is that thing doing that? Is that real? Hey, everybody. That's what they sound like. Yay! All right, we gotta find the elephant one because he made like a really big one. Whoa, what? I'm not gonna comment. Okay, let's. Yeah, I want to see this one. Look at that. That looks like something out of Metal Gear Solid. I did, Justin. I saw that video with Adam Savage where it was pulling the pulled him in a carriage. Look at that thing. What? A weapon to surpass Metal Gear. Yeah, Strand Beast, that guy, he does some really cool stuff. All right, everybody. I'm gonna eat some food. That is my next objective. It's been a pleasure hanging out with you, looking at these strange and terrifying robots. Mostly terrifying. Jeez. See you later, Joe. See you guys on Friday. It's been good. I'll send back a little Z. Wait, what's the big Z again? Wait, what? Oh, that's funny. All right, people.